I'm literally holding my coffee cup right now. And it feels completely solid, right? Like totally stable.
Right. It feels like a solid object.
But the crazy thing is, the cosmic forces keeping the ceramic from just, falling apart into a cloud of loose particles, they actually operate completely backward.
Yeah, it's backward compared to basically every other force we experience.
Exactly. So today's deep dive is into quantum chromodynamics, or QCD. We're looking at the physics of the strong interaction, right?
Right.
And our mission today is to explore how the absolute tiniest building blocks of the universe function in ways that just defy common sense. And, well, what that reveals about humanity's incredible capacity to decode reality.
It really is incredible because to understand why your coffee cup doesn't just dissolve, we have to look inside its protons and neutrons.
Right, down into the really tiny stuff?
Exactly. Those are made of fundamental particles called quarks, which, fun fact, physicist Murray Gell-Mann actually named after a totally whimsical line in James Joyce's novel Finnegan's Wake.
Oh, wow, I love that. From a novel.
Yeah. But to mathematically model how these quarks behave, physicists ran into an immediate problem.
Wait, before we solve that quantum problem, I should do a quick note for you listening. If you need help with AI training, automation, integration, or software development, you should check out our sponsor, Embersilk.
Oh yeah, they do great work.
Right. If you're trying to uncover where AI agents could make the most impact for your business or personal life, embersilk.com is your go-to resource for all AI needs.
Perfect. So returning to those quarks, the mathematical problem they had was about charge.
Like a electrical charge.
Kind of, but with electromagnetism, we just have two charges, positive, negative. But the math for quarks required three distinct states to balance out and form a neutral particle.
Oh, weird. So they needed a metaphor for a property that comes in three primary types that combine to make a neutral whole, so they called it color.
Exactly. It has absolutely nothing to do with visual color or, like, a box of crayons.
Right. It's purely a mathematical naming convention.
Yeah, just math. And those color-charged quarks interact by basically passing these force-carrying particles back and forth.
And because these particles literally glue the nucleus together, they were named gluons.
Which is a very literal name, yeah.
I mean, physicists sometimes get right to the point. But okay, so the gluons are managing this color force. But going back to how this operates backward, if I take two magnets and pull them apart, the magnetic force drops off, right?
Right, it gets weaker.
And gravity does the same thing the further away you get.
Yes, exactly.
But the strong interaction does the inverse.
It does. It's a phenomenon called asymptotic freedom, which actually won the Nobel Prize in Physics back in 2004.
Wow. Asymptotic freedom, that sounds like a sci-fi movie.
It really does. But it just means that when quarks are practically touching inside a proton, they barely interact at all. They act like free particles.
Wait, so they're just like hanging out loosely when they're close?
Exactly. But as you try to pull them apart, the interaction strength rapidly increases.
Okay, so it's like a rubber band.
Yes, perfect analogy.
Like, when it's loose, there's no tension. But you pull the ends apart, and the resistance fights back harder the further you stretch it.
Exactly right.
Wait, but if the force keeps increasing as I stretch this quantum rubber band, eventually it has to reach a breaking point, doesn't it?
You would think so, yes.
But if it snaps, I wouldn't just get a lone quark, would I? Because the tension in that stretched field represents an enormous amount of stored energy.
Right. And think about Einstein's equation.
Oh, E equals mc squared. Energy and mass are interchangeable.
Exactly.
So the snap doesn't just break the bond. The pure energy of that snap converts into physical mass. It creates a brand new pair of quarks right on the spot.
It is mind-blowing. The field literally creates new particles out of the tension.
That is unbelievable.
Yeah, you apply energy to separate them, and that very energy births a new quark to instantly partner with the one you tried to pull away.
So the system immediately stabilizes itself.
Right. It's a concept known as color confinement. The universe simply does not allow a quark to exist in isolation.
So no matter how hard we try to isolate the building blocks of reality, the universe's mechanics automatically generate new pieces to ensure they always remain connected.
It is a beautifully self-sustaining design. It guarantees the physical stability of everyday matter.
That is so incredibly elegant.
And the best part is, we figured out these mechanics using mathematics long before we had the supercomputers to fully map the interactions.
Which just goes to show you, if we can mathematically model invisible fields of energy snapping into physical matter, the ceiling for human discovery really is limitless.
It absolutely is.
It leaves you with this incredible thought. If the fundamental grammar of our universe is built on energy spontaneously creating mass to maintain stability, how might humanity eventually harness that exact mechanism to power our future technology?
Oh, the possibilities are just endless.
Just think about what we can build when we learn to engineer with the very forces that refuse to be broken. The future is so bright.
It really is.
Well, if you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.